Before we go much farther with PLCs, so I have to teach you how to count. You might say, well, I've been counting since grade school. I don't think there's much I can teach or that you could learn that you don't know. Well, let's find out. Let's see what you know and what you don't know. So we're going to talk about numbering systems and various codes. We'll start off with the decimal system, which you're already familiar with. You may not think about it, but actually there are 10 different numbers. There are only 10 numbers in a base 10 system. Those numbers are 0 through 9, right? Those are the digits that we use. If you say, yeah, but what about the number 10? Well, 10 is a 1 and a 0 together. And what we agree on is that the positions have different values. For example, if you wanted to make money, right, you want to make a lot of money, and so if I offer you $10 per hour, that might be, well, not too good, but if I offer you $100 per hour, you'd probably jump on that in a heartbeat, right? Because that represents $100. That 1 is in the hundreds place, and you may not have thought about the place value of the system we use much, but you can actually calculate the place value very easily. The 0th place, now be careful, all numbering systems have to start from 0. You have to start counting from 0. I feel sorry for my daughter. Back when, she's the daughter of an engineer, and so back when she was very young and we were playing Candyland and board games and things, I was trying to teach her some basic things that would help her later, and so I always made her count the squares from 0, so you didn't just count, you know, pick up your piece and count 1, 2, 3. You counted 0, the square you were on, 1, 2, 3, 4, etc. So we'll see if that sticks or not. But every numbering system begins at 0. So this is the 0th column. The ones place is what I would call the 0 column of the number. The tens place is the 1 column. And the hundreds place is the 2 column, and so on. Now, why do I call it that? Well, because you can calculate the value of each column by simply raising the base, which our base is 10, to the power of the column number or the position. So 10 to the power of 0 is 1, right? 10 to the first power is 10, 10 to the second power is 100, and so on. And that allows you to calculate the value of each column, each position, as a function of the number of the position. You just take the base, because we're using 10 numbers, and there you have it, right? Take it to the power of the position. So how do we have 10 numbers when those numbers are 0 through 9? Well, count them. I mean, the numbers are 0, there's your first number, right? All the way through to number 9. That's the 10th number. And so, in fact, base 10 uses 10 numbers, and those numbers are 0 through 9. Now, to calculate the value of a particular position, you take the base itself, which is the number 10, or not really the number 10, right? The value of 10, and you raise it to the power of the position. So, if we have a number like 1962, well, 2 tells you how many ones there are, 6 tells you how many tens, 9's how many hundreds, and 1 is how many thousands, and you probably remember this. So that's the base 10 numbering system, but it's probably not really the way you would think about it. So at least not since grade school, right? So to calculate the value of this number, you've got 2 ones, 6 tens, 9 hundreds, and 1,000. Add those all up together. Not surprisingly, we get 1,962 in base 10. Notice that there is a 10 at the lower right-hand corner to differentiate this number from any other number that may have a different base. At this point, you probably don't really see why that's important, okay? But it is. So we're going to start, when we need to, for clarity, we're going to start using a subscript after the number to indicate the base that that number is, well, predicated upon, that it relies upon, that you should interpret it through, okay? So this is called the radix, or the base of the numbering system. And it just tells us how many numbers we have to work with, and once we're out of numbers, like we start from in the ones place from 0, go all the way up to 9 as we increment. Once we're out of numbers, we have to have a new position. Notice that's what happened. You count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you're at 9, and you want to add one more to it so it overflows. In other words, you put a 1 in the 10 position and roll back over to 0. On older speedometers, you would see this happen. Well, not speedometers, but odometers. You would see this happen where the mile would go from 0 all the way up to 9, and then it rolls back over to 0 while the next position goes up 1. And that's exactly what we're doing here. The binary system is a little bit different. The binary system says, well, why do we need 10 different numbers? What if we only had 2? And why would we only want 2? Well, base 2 is binary, not surprisingly, bi means 2, right? Why would we want to consider such a system? I mean, after all, we're all used to 0 through 9. Well, the reason is because inside of computers and machines that are, digital electronics, there's only on and off, and that represents a 0 and 1. That's 2 different digits, 2 different states, if you will. Okay, 2 different numbers. And so in digital circuits, it's convenient to talk about the number 0 being low, for example, the number 1 being high. Okay, now we can turn that around if we want, but most of the time that's the way we think of it. So we can think of this as on, off, high, low, 0, 1, set, reset. All these things are synonyms for on and off. Okay. Now the binary system only uses 2 digits, so how on earth would we count with it? Well, let me help you out here. Like I said, I want to teach you how to count. If I hold up one hand, I've got 5 fingers on that hand. How much can I count up to? How much can you count up to with 5? I mean, the joke is, yeah, if you give me more than 10, I'm going to have to take off my shoes and use my toes to help me count, right? That's the joke you may or may not have grown up with. But in fact, I can count well above 20 on one hand. Let me show you how. I'm going to define each digit, rather than being an increment of 1, I'm going to define them as positions. So let me turn my hand around. It's easier for me to think of it that way. And that should make it the correct orientation for you, where my thumb will end up being what's called the least significant bit, or the least significant digit. By the way, you'll hear me use the word bit. That comes from binary digit. It's a compaction of the two. It's just squeezing the 2 words together. So when I say bit, I mean a binary digit. So here's one binary digit, here's another, here's another, here's another, here's another. I can either have them on, as they all are right now, or off. Okay, so let's begin counting. You always start at 0. There's 0. Okay? All digits down. Now, one thing to note about the binary system is that there's only 2 values, right? There's either off or on. So what could I do from here? Well, since this is the lowest value, my thumb's the lowest value, there's 1. Okay? 0, 1. Now, to represent the next number, I'm actually going to put my thumb down and bring my finger up. So there's 2. To represent 3, I'm going to turn my thumb on again. Okay? So that's 3. Now, pardon me, forgive me for the crude sign, but the next number, I'm out of digits here, right? I went from 0 to 1, and I was out of room, so I overflowed and went to 1 here, like a 1, 0 now, you see. And then I went to a 1, 1, but I'm out of space again. So forgive the crude gesture. This is not the normal sign, right? To us geeks, this means what? 0, 1, 2, 3. It means 4, right? The next number is 5. Do you see that? I'm going back to the least significant digit. Notice that it is turning on and off in sequence. What's next? Well, you might have guessed. There's 6. There's 7. Here is 8, though it's hard to get. It's my ring finger. Okay? So there's 8. Here's 9. Here's 10. Here's 11. Here's 12. There's 13. 14. 15. And now I'm out of digits again, and so finally, there is 16, you see? So it looks like I'm either trying to learn some odd version of sign language, or maybe I think I can make gang signs. I don't know. But you see how I'm counting. As a matter of fact, we were at 16 here. Let's see how far we can go. 16, 17, 18, 19, 20 is kind of hard to get. There's 21. There's 22. Okay, 23. And let's see. Now I'm out here, so I can raise this one again. So 24, though it's hard to keep up. I'm going to use my other hand. 24, 25, 26, 27, 28, 29, 30, 31. So I can count from 0 to 31 with one hand, with only 5 digits, by instead of just using, assigning 1 digit per number, per count, I will assign 1 digit per position and use binary, on and off, where, each one can be individually on or off, although some of them are pretty hard to get with my hand. Fortunately, I played piano for a while, so that seems to help me a little bit. Anyway, so now you can see how this works if you look at the screen. A decimal 0 can be represented as the same number, binary in 0. A 1 in decimal looks just like a 1 in binary, but a 2 in decimal looks different, because notice we're out of space, right? We went from 0 to 1 already in our first digit. We need a new digit to the left, and so we make a new bit and turn it on, and that is 2. Turn both of the bits we've already got on. That's 3. We're out of space again. We need another bit. There's 4. You see 5, 6, 7, 8, 9, 10. We could go all the way to 31. Of course, in this particular image, there are only 4 different bits. And I have, of course, 5 bits on my hand. It's really important to remember that all numbering systems begin at 0. So how would we convert a binary number to a decimal number? Well, we have to understand that in a binary number, each of the digits have a value. For example, what you do is you always take the base to the power of the position. Okay, so if you want, back in decimal, if you want the value of the very 0th column, you take 10 to the 0. Well, that's just 1. Okay, so that's the value of the lowest digit in decimal. In binary, the value of the lowest digit is calculated as the base, which is 2, to the power of the position. It's still the 0 column. It's still the 0 position. So 2 to the 0 is 1. Therefore, that lowest digit is the ones place, just like it is with decimal. Unlike decimal, though, where the next digit is the tens place, in binary, the next digit is 2 to the power of 1. It's the next column over. So it's the 1 column, okay, or the 1 position. So 2 to the first is 2. So this thumb had a value of 1. The finger had a value of 2. So if that was on, it means 2. So I can easily make 3 very quickly because I know this is worth 2 and this is worth 1. 2 plus 1 is 3. Okay? The next position, the middle finger that I had, that is the second column. Well, it's not the second column, it's the 2 column. The second column is 1 over. So it gets a little confusing. That's why I call it the 2 column instead of the second column. See, it's actually the third one over. So 2 to the second power is 4. So this was the 4's bit. When it's on, remember I made the odd sign, right? When it's on, that's 4. I can make 5 easily by simply adding 1 to it. Right? So there's 5. I can make 6 by adding 2 to 4, right? The order increases. So basically, the next column over, you just take 2 to the power of the next column and so forth. So you can count it easily. This is the 1's place, the 2's place, the 4's place, the 8's place, and the 16. So it's really easy. If I want to represent the number 16, there we go. If I want to represent the number 17, no big deal. How about if I want the number, oh, I don't know, 24? Well, there it is, because 16 plus 8 is 24. Okay? So you just have to decide which ones of these you need to turn on. So the way I do this in order to convert from decimal to binary is a little different than what you'll see on the next slide. But for right now, let's look at converting a binary number into a decimal number, into a number that makes a little more sense to us. Because if I tell you that I want you to work a problem and I give you a number that is 1010101, like you see here, in base 2, you're going to be scratching your head wondering, how big is this number? Is this a big number? Is this a small number? What number is it in base 10? I don't recognize these numbers well like I do base 10 numbers, because of course you haven't been working with base 2 numbers all your life. You've been working with base 10 numbers all your life. Well, we can calculate the value of each position, and the 1 or 0 just tells us if that position is contributing value to the total number or not. For example, the column all the way over on the right has a 1 on. So what that means is that we do have whatever is in that position. That position is the 1's position. 1 times 2 to the 0, which is the 1's position. 1 times 1 is 1. So we have a 1 to add to the number. But the next column over, which is the 2's column, because 2 to the first is 2, has 0 of them. Right? There are no 2's. And this is the same thing you do in decimal. Remember the number we had in 1962. The 6 means that you got 6 tens. In the same way that a 1 in the 2 column here, I'm going over to the 3rd column by the way, a 1 in the 2 column indicates that you do in fact have a single 4. Okay? Now you might scratch your head and say, well, with 16, 8, 4, 2, and 1, that seems pretty limited. Could I actually represent any number from 31 down? Well, as a matter of fact, you can. You saw me count them off. But how do you go the other way? Well, we'll get to that in just a second. Let's finish this one off. So let's see. We have a 1, right? That's what the first or the 0 column tells us. We don't have a 2. That's the next column. We do have a 4. In the 3 column, that there's a 1, so that indicates we do have an 8. We don't have a 16 from the 4 column. We do have a 32 from the 5 column. We don't have a 64, and we do have a 128. So you see what we're doing here as we multiply them out. 1 times 1 we get a 1, 0 times 2 we get no 2's, 1 times 4 we get a 4, 1 times 8 we do get an 8, 0 times 16 we don't get a 16, that contributes 0 to the sum. 132 we do get a 32, we don't have any 64's, and we do have a 128. Add up that whole column, and this number that is a binary number base 2, you see the subscript on the right, that number in decimal is 173. So it's just the sum of the products is all it really is. Okay, so you can convert from binary into your decimal equivalent. Okay. Now each binary number is known as a bit, as I said, and a lot of times the way it's set up in computers and PLCs and even your smartphone and any digital electronic device you have, the way it's set up is in bytes. Now I guess that programmers were hungry, because when these things were named, a bit sounds like something you can eat, right? Just to give me a bit of something, or a byte sounds like you're going to take a bite out of something, but it's spelled B-Y-T-E instead of B-I-T-E. I don't know why that is, but that's the case. Did you know that 4 bits together, half of a byte, also has a name? It's usually not told to students, I guess, because it's not as useful as others, but sometimes it is useful. It's called a nibble. So 4 bits is called a nibble. So bit, nibble, byte, and then after that you kind of get out of the hungriness, I guess. By that time, I guess programmers were making money and could afford food, so weren't so hungry anymore. If you put 2 bytes together, which is pretty common, so you have 8 bits plus 8 bits, that's called a word. If you put 2 16-bit words together, it's called a long word. And then the names kind of, they're not quite as well agreed upon after that. It just depends. And a lot of times, maybe you have a computer and you know that your computer is a 64-bit computer. What that means is that the processor is able to deal with 64 bits at one time. Now, it doesn't necessarily mean that the memory is set up that way, although I think today memory is 64-bit. I don't know. I haven't really kept up with it. But what it means is that computers work with on-off switches, and it's not very useful to have a single on-off switch, and so we commonly group them together in these ways. And when you have the computer go and read a memory address, what it typically is doing is getting a whole word, or if it's grabbing 32 bits or 64 bits, however much it grabs all of that at once. A lot of PLCs are still 16-bit or 32-bit. You can even find an 8-bit PLC if you really wanted to, and they're still useful these days. But some other terminology here, since the lower byte, look all the way on the right of the slide, the lower byte has the least significant bit, right? Remember, that's the 2 to the zeros. Just like if you were looking at a number that represented dollars, right? So let's say you $52,368, okay? Well, the 8 is only $8. The 5 on the other end, though, that represents something much more significant. That represents 5 10,000s. That's the part you probably care more about, not the $8 on the end, right? So in the same way, this least significant bit contributes the least to the number. It's just a 1. The next one over is a 2, then a 4, then all the way over to the most significant bit. And I'll let you calculate the value of that position. It's pretty easy. That position, although there are 16 bits here, that's the 15 position, or the 15 column. And so you'd raise 2 to the 15th power, and that's the value of that most significant bit. If it's on, that's how much gets added to the total number. That's the contribution to the total number. So the way that PLC memory is organized is by either bytes or words or double words, what I call long words. It just depends on the processor more than anything. But this might explain something you may have noticed whenever you had an older computer. Older computers typically didn't show you a nice splash screen, and even today a lot of times you can turn that off and see what it's kind of doing. There's something in the computer called BIOS, or CMOS, or the Basic Input-Output System. There's another one, EFCI or something like that. I've gotten out of my computer knowledge is growing old now, because I don't do as much with them as I used to in terms of fixing, repairing, learning about the latest stuff and so on. But it still is based on the same thing. So older computers, what you'll see when you turn them on is you'll see this memory check that goes up, and you'll see it count up and up and up. And in the old days, you'd add memory to your computer and you'd see it count up, and it would go to it seemed almost like magical numbers. There were certain numbers it would always go to, like 128 or 512 or 1024. You might wonder why that is. Well, the reason for it has to do with the way that memory is addressed. And so if you want to say, well, I need to store a number for my program, like, the level in a tank. Okay, so you could represent the level in a tank with a 16-bit word and have quite a decent number of positions. By the way, a 16-bit word would give you 65536 different levels from 0 to 65535, which would be pretty good resolution for most tanks to have that many different step sizes, and we'll talk about resolution later. But if you have that in memory somewhere, 16-bit somewhere that represents the level in the tank, you probably need to go and either write that level or read what the level is or whatever the case may be. Well, how are you going to talk about that address versus some other address? Well, you could number the addresses, and since we're talking about computers, why not number them in binary? And if we're going to number them in binary, and we're going to use bits to address these things, let's not waste any bits. And so if you only have 4 bits, how many different memory addresses can you access? Well, there are 16 addresses, 0 through 15. If you add one more, now you can access 32 different addresses, address 0 through address 31, and so on and so forth. So by adding a single bit, let's see, if you go all the way up to 8 bits, let me do it this way, 8 bits, then you can access 256 different addresses, address 0 through 255. And it just keeps doubling every bit you add. And so in a computer or a PLC, when they say 1K of memory, what they really mean is 1024 different memory addresses. And the reason for that is because this bit thing, the fact that if we add a bit so we can have more memory, we may as well use all the different possible combinations of the bits and have that much more memory. So finally, how do we convert a decimal number to a binary number? Well, there's 2 ways of doing it. Well, 3 I can think of right off. There's a really easy way, which I'm not going to tell you until we're in lab. There's a super secret program on your computer. It comes with all the computers I know of, and you can use it to convert between any of the bases I'm going to show you. But decimal and binary, it can do like that for you. Okay, I'll show it to you in lab. But for now, one way to do it is to just say, okay, I've got a number. Let's start with this one, 47. I'm not going to use the method that's shown on the screen here. I've got 47, I want to represent it. Well, let's see. 5 bits, the biggest number I can represent is 31, right? So I had the 16s place plus the 8s plus the 4s plus 2 plus 1. That's 31. That's not big enough to represent 47. If I add one more bit, well, then I've doubled the number of numbers that I can represent. Now I can represent 64 different numbers. Those are 0 through 63. Since 63 is bigger than 47, this will work. Okay. As a matter of fact, the value of this latest bit that I've added is not 1, 2, 4, 8, or 16. It is 32. So I'd like to add 32 to my repertoire. I'd like to be able to put a 32 in there. Well, I can, right? In fact, 32 is the bulk of 47, and so if I say, well, I'm going to turn on the bit representing 32, well, how much does that leave out of 47? Well, let's see. 47 minus 32 would be 15, right? Okay, so I've got my 32 is on. I need 15 more. Well, if I turn on 16, that's too much, right? That'd be 48, so I can't turn that one on. So let's see, instead I'll turn on the 8. Okay, so now I've got a 32 over here and an 8. That's 40. I'm getting close. I just need 7 more. Could I get a 4 out of that 7? Yeah, so let's turn on the 4's place. Well, let's see, 4 from 7, that leaves 3 more that I need. Could I turn on the 2 and not overflow, not make a number bigger? Well, sure I could, because all I need is 3 more, so turn on the 2. 2 from 3 leaves me with 1, so I turn on the 1. So there it is, right? The number from least significant to most is 11101. In fact, that's what you see here. From least significant to most significant, 111101. Because I know I need the 1's place on, I need the 2's, the 4's, the 8's, not the 16's, but I need the 32's place on, and that will give me the decimal number 47. Okay, that was interesting, but what about this method? Well, this uses what's called the Modulo Operator, or Mod Operator for short. And what you do is you simply take the number and you divide by 2, and the remainder tells you whether or not the bit is on or off. So 47 divided by 2 is 23 almost. There's a remainder of 1, right? So just take the remainder and put it into the least significant digit, okay? Then take the 23, the number you had before, divide it by 2. Well, that's about 11. Of course, it's 11 and a half, but we can't have halves. We have to work with integers here. So 23 divided by 2 is 11 with a remainder of 1. So put the 1 into the next significant bit. Take the 11, divide it by 2. Okay, that's 5 with a remainder of 1. Take the 5 divided by 2. That's 2 with a remainder of 1. Take that 2 divided by 2. That's 1 with a remainder of 0. And then take the 1 divided by 2 is 0 with a remainder of 1. Because we can't end up with a fractional number here. We need a whole number, right? So there it is. We're out of it. We didn't have to figure out how far to go this time. We just started dividing and dropping the remainder into the bit number, and this works. I won't prove to you how or why this works. I think you can figure it out. And if you can't figure it out, ask me. I'll give you some hints on how it works. It's a pretty clever and interesting little thing. So computer memory is really just a series of binaries, zeros and ones. And the way you address it depends on the particular PLC. Obviously, it has a binary number internal to the PLC that represents that particular location. But a lot of times there are names for these things, like Y's are outputs, but Y's really just refer to memory addresses. X's are inputs. But again, the actual value of the inputs are measured by electronic circuit and then copied into memory. So there are memory addresses that are associated with all your inputs, all your outputs, timers, counters, all the different bits that you would use for remembering events in PLC programs. These are all just a bunch of ones and zeros. Okay. Now, when you have a particular input card, so say that you have the PLC doesn't have enough inputs and outputs by default, so you add another card to it. What you'll notice is that these cards often have either 8 or 16 or 32 or 64 inputs. The reason for that is because that fits nicely with just one whole word, either an 8-bit byte, for example, or a 16-bit word, or a 32-bit double word or long word, and even in 64-bit, a 64-bit. Now, some cards actually have more than one word associated with them. When you start to get up into the 128 input cards, then it's got to be broken up into multiple words. But each flavor of PLC has its own name for these things and way that you address them. But you'll notice on the input cards that they are always multiples of 2, and this is the reason why. And basically each bit in a word can represent whether one input point is on or off, assuming that that input point is a digital input or output point even. Okay? So here's the joke for you. There are 1-0 types of people in this world, those who understand binary and those who don't. So someone who hasn't learned about binary will look at this and say there are 10 types, those who understand and those who don't. Wait a second, there's 2 types. What do you mean? Well, this is, of course, binary too, right? Because you got the 1's place, there's no 1. You got the 2's place, there is a 2. And so if you understand binary, you will understand this joke. The octal system is a little bit different than the decimal and binary system. Remember, we went from the decimal to the binary system saying, well, what if it's not convenient to have 10 different numbers? What if it's more convenient to have 2 because we're working with switches? Well, sometimes it's convenient to have 8 different numbers, and thus the octal system. Now, those numbers will be 0 through 7 because we always have to have 0 in our numbering system. And if you count the number of numbers from 0 to 7, there are 8 different unique numbers. Now, it's interesting to note what happens. In decimal, you don't overflow the position until you reach 10, right? 0 through 9, and then we don't have any more numbers. So we need another digit. In binary, we overflow almost immediately because, we go from 0 to 1, and we're out of space in that bit, that binary digit, and so we have to include a new digit. And so you can see counted in binary here. Octal is interesting because it breaks at 7, right? Because 8 and 9 are not allowed. We only have 8 numbers. So you go 0, 1, 2, 3, 4, 5, 6, 7. The next number, you're out of numbers. So that position has to roll back over to a 0, just like an odometer would roll over in that position. Of course, odometers use base 10 numbers so as not to confuse everyone. But we'd roll from 7 over to 0 and then increment the next digit to a 1. And so you notice that we then continue. What looks like 10 to you actually represents the number 8 in octal. Okay, so I should say that again. The number that looks like 10 in octal is actually the number 8 in decimal. So we go 1 0, 1 1, 1 2, all the way to 1 7. Guess what? We're out of space again. The 7 can't go any higher, so it rolls over to 0, and the digit next to it increments, and so on and so forth. Alright, so a lot of times PLCs are based with, or input and outputs are based with octal addressing. And the reason for this is because the way it breaks up is kind of nice. 0 through 7 breaks up nicely as a byte, right? So there's 8 data bits that make up the byte, and thus octal addressing is often used, although it's usually not really obvious that it's octal addressing. Now sometimes it is. Sometimes what will happen is you'll see an input slot on a PLC, and these are usually older PLCs. Modern PLCs don't do this as much, but older PLCs, what you'll see is they're numbered 0, 1, 2, 3, 4, 5, 6, 7, and then it goes 1, 0, 1, 1, all the way through 1, 7, and if it continues after that, it starts over again with 2, 0, etc. And so it's pretty common to see this in older PLCs, and especially PLC 5 by Allen Bradley, which is a pretty old PLC. Some others use it as well, and so it's worth knowing about this. Now the nice thing about octal is that it's kind of convenient in handling bigger binary numbers. I mean, if you have a binary number that has 8 different bits, it's kind of hard to write it out because you have to write 8 different things, ones and zeros. Whereas obviously decimal has the advantage over that because it's more compact. But decimal does not translate to binary very easily. They don't break at the same point. What do I mean by that? Well, in the octal system, you can express 3 binary digits with one single digit, because look at binary. We've got 000, 001, 010, 011, and then we've overflowed 100, 101, 110, 111. We're out of space in binary. If we want to add one more to it, we need another digit. But look at what happens to octal. Octal during this time maps to 0, 1, 2, 3, 4, 5, 6, 7, and look what's happened. This is actually really nice. Binary overflows into its 4th decimal place, or digit, I should say, because it's not a decimal, it's not a base 10. It's octal place, I guess. Whereas, it's binary place. Whereas octal rolls over to its 2nd octal position, right? So this is actually really nice because it can represent binary very nicely. 3 bits correlate nicely to just one octal number, and that is always the case. It makes it easy to transform a binary number, say, into an octal number, because all you got to do is break up this long string of 1 zeros that represents the binary number into sections of 3 bits, and each one of those bits will simply transform directly into an octal number. Now, what about transforming between octal, which is kind of hard to understand, to base 10, which we all understand? Well, notice that we've got 462 written as an octal number. It's base 8, so there's the subscript of 8. Now, to calculate the value of each position, it's just like it is in the binary and the decimal system. You just take the base, which is base 8, to the power of the column number. So the column number is 0, so 8 to the 0 is 1. Again, we have a 1's position. That 6 in the 462 is in the 8's position, okay? And then the 4 is in the 64's position. So we can say how many 1's we want, how many 8's, and how many 64's. Now, until you're used to this, you might look at it and say, well, this seems very limited. I don't know how I would represent a number like 27. Well, actually you can, because now you can say how many 8's you want, right? Well, let's try that one just for fun. Let's see, we got 1's, 8's, and 64's. 27 doesn't need a 64, so all I need is 2 different octal digits in order to represent 27. And all I got to do is figure out how many 8's there are in 27. Well, let's see, 8 and 8, 16, and 8 is 24. One more 8 would drive me over to 32. So apparently I need 3 8's, right? 3 8's is 24. And I need, let's see, to represent 27, let's see, 24, 27, difference is 3. I need 3 1's. So 3 8's and 3 1's, 3 3 subscript 8 is the same thing as 27 subscript 10. This is kind of fun because you can show people that, numbers equal each other that don't look like they should, like, I don't know, 33, as I just said, equals 27, but they're different bases. So you interpret the number differently. So what about converting 462 into decimal? Well, the 2 says that we have 2 ones, 2 of 8 to the 0 power, so that's 2. The 6 says that we have 6 8s because it's 8 to the first power, so it's 6 8s or 48. And then the 4 says that we have 4 8 squareds, or 4 64s, which is 256. Add those all up together and you get 306. So this 462 in base 8 is equivalent to 306 in numbers that we're used to in decimal. So you can see here how that 462 converts to binary really easily. All we have to do is take the 2, break it out into 3 binary digits, and all we got to do is think about, well, let's see, we want a 2. So if I have 3 binary digits, I'd have the 1s, the 2s, and the 4s. Well, that means just leave the 2 on, so that's no problem. Okay. How about the 6? Well, to represent 6, I need a 4 and a 2. So there we go, 1 1 0. And I'm probably doing this backwards from your view, I apologize. The 4s, let's see. Well, let's see. Here's the 1s, the 2s, the 4s. So there's a 4. 0 0 1, or I'm sorry, 1 0 0 would be a 4. And so it's easy to convert these octal numbers into binary and the other way back as well. Now the hexadecimal system, you might have surmised by this point that hex is 6, decimal is 10, so it's 6 and 10. So it's a 16 base system. And let me show you how this works. Instead of restricting ourselves to the numbers 0 through 9, we're going to add some more numbers in, and those numbers are A, B, C, D, E, F. And you say, wait a second, those are letters. Well, you have to let go of the idea that these are letters. I don't know if you guys like Dr. Seuss, but I grew up on Dr. Seuss, and I'm trying to grow up my daughter on Dr. Seuss as well. One of his books was On Beyond Zebra. I don't know if you ever read it. It wasn't necessarily one of the most popular. Certainly wasn't Cat in the Hat or any of those. It was an interesting book because the character was writing out the letters of the alphabet, A through Z, and they were getting bored with these letters. We only have 26 letters in the alphabet. What else could we write? So they started drawing all kinds of crazy characters indicating other letters that you can make odd sounds with and so forth. That's basically what we're doing here. We're kind of bored with 0 through 9, and they don't map nicely to binary. So what about if we add some more numbers? So A to F are symbols that you're already familiar with, but now we're making them into numbers. Now this is not like what you did in high school where you learned about variables and the letters took on a variety of numbers. No, rather this A through F represents very particular numbers. A is the number that comes after 9, B is the number that comes after A, and so on and so forth until F. And by the way, we don't use G here. We only need 16. And if you count the numbers we have now from 0 to F, since F represents 15, we have 16 different numbers. They are 0 through F. Now the nice thing about it is that these hexadecimal numbers translate very nicely into binary. So over there in the binary column, what you'll notice is 0 in hexadecimal is 0000. Okay, and then 1 is 0001. That makes sense because in the binary number, that position is the least significant bit, which is the 1's position. This is kind of boring. Let's jump up to the, I don't know, to the 8. The 8's pretty easy because, let's see, in the binary number we've got the 1's, the 2's, the 4's, and the 8. Sure enough, the 8's position is on. And so binary 1000 is not the number 1,000, it's just 8. So if I tell you, I'm going to give you 1,000 base $2, I've only promised you $8, right? That's not as exciting as it looks on paper. And of course, it's just simply 8 and decimal. As a matter of fact, hexadecimal and decimal match all the way up to 9. Now in decimal, we're out of numbers at 9, right? We don't have any more numbers, so we have to roll over that digit to a 0 and get a new digit. Whereas in the hexadecimal system, we're not out of numbers yet. The next number is A. As a matter of fact, notice the binary system also is okay with 4 bits, right? There's still some space here. We can turn on the least significant bit to get to 9, and then after that, turn on the 2's place, turn off the 1's place, and let's see, 8 plus 2 is 10. So 1010 is simply 10 in decimal. And what you'll notice is as you get all the way down to E, which is 1110, or in other words, 8 plus 4, which is 12, plus 2 is 14, then the next number after that turns on the 1, which is 15, which is F, and look what's happened. while we're not out of space in decimal, we are nicely out of space in binary. You see that? We've got 1111. If we want to go up any higher, we need another digit. In the same way, hexadecimal has just run out of numbers. It's at F, it needs to go back to 0, and it needs a new digit, a new hexadecimal digit. And so binary and hexadecimal match very nicely. As a matter of fact, hexadecimal matches binary better than octal matches binary, because if you think about the way we normally break up bits, we've got, you can have one bit on or off, the next is a nibble, 4 bits, which nicely it can be represented by one hexadecimal digit. After that, 8 bits, which is really just 2 nibbles, so that would be 2 different hexadecimal numbers, right? And we use it, from there we just add multiples of these, right? After 8 is 16, 32, and so forth, and that will always break down nicely into groups of 4, where each group of 4 can be represented by a hexadecimal digit. So this is a really nice mapping for binary. In fact, hexadecimal is something you've probably seen and may not have known what it meant. Do you remember when your computer blue screened? Did you ever see that? Yeah, I think blue screen started back in Windows, I think it was Windows XP or 2000, something like that. Anyway, the blue screen of death was where, the computer just crashed and you lost your work probably. You might have said a few choice words. And maybe the numbers that came up on the screen looked like the computer was saying a few choice words, because usually it was some numbers and then XO. And you probably were left scratching your head wondering what all this meant, and was there some way to get your data back? Is somebody going to look at this at Microsoft and say, oh my goodness, his computer crashed, why did this happen, and actually figure out what went wrong? Well, actually probably not unless enough people complain and enough people, computers crashed from this. Computers can crash for all sorts of reasons. Overheating is one. Bad memory is a very common problem. In fact, if you don't use MTest, I think MTest 86 Plus is the one I used to use, and I guess it's still a good one nowadays. But I've found a lot of bad memory that was the root of the problem for computers crashing and blue screening. But the numbers that were being displayed were in fact numbers that could be used for diagnosing the problem, but they were written in hexadecimal, and that X was used to indicate that the number was a hexadecimal number, I guess using the X from hex. Okay? And it's just a quick abbreviated way of indicating to the user that, hey, this is a hexadecimal number, this is not a base 10 number. It's also interesting, you don't have to restrict yourself to hexadecimal. You could have as many characters as you really want. If you look at YouTube URLs, the Universal Resource Locator, the address, you'll notice I think it's an 11-digit number that it uses, and it uses all sorts of things in it. There's some underscores, there's dashes, they don't use question marks. They use all the numbers and all the letters, if I remember right, uppercase and lowercase. So you might want to, just for fun, figure out what base system they are using by looking at a few YouTube URLs, and then figure out how many different videos they can access with only 11 different digits. And I think it's 11. You might have to count it. I might be off by 1 or 2. I'm pretty sure it's 11 digits they've got. So they got all your lowercase, so there's 26. All the uppercase, there's 26 more. Plus all the numbers 0 through 9, there's 10 more numbers, plus underscore and dash. And we're getting into quite a few videos seeing that each one of those digits can go all the way from lowercase letters through uppercase letters through numbers through underscore and dash, and maybe some others that I've forgotten. Okay, it's quite a few different numbers that can be represented by one digit, and if you have 11 digits, that's quite a few videos that they can give a unique locator to. So, very commonly in PLCs, we do use the hexadecimal number system, and a word of data consists of 16 data bits, so it's really easy to convert a hexadecimal number into a binary number, because again, those 16 data bits can be grouped into, or broken up into 4 groups of 4. But what would we do if we had to convert hexadecimal into decimal? Well, it's the same thing we've been doing all along. All you've got to do is take the number times the base to the power of the position. So we still have a ones place. We have a 16s place now, and then we have a 16s squared place, which is a 256s place. We can have 16 different counts of 1. We can have 16 different counts of 16 and 16 different counts of 256s, okay? So in this particular number, 1B7, we have 7 ones. We have B16, so you got to go back and figure out if we want to go to decimal. What is B? Well, it's actually 11. A is 10, B is 11 in decimal. So we're going to do our math in base 10. So that's 11 16ths, which is 176, and we have 1 16 squared, or 1 256. So we have 7 plus 176 plus 256 is 439 in base 10. What you'll notice is when you use a base that has fewer numbers than base 10, the number gets long. It looks bigger. Okay, so an octal number will look like it's farther along than the equivalent decimal number. If you write your age in octal, for example, it'll look like you're older. If you write your age in binary, it'll look like you're very old. But if you write your age in hexadecimal, you make yourself look younger. And so it's kind of interesting. As a matter of fact, my age right now is 46. If I were to figure out my age in hexadecimal, what would I have to do? Well, I got to figure out how many 256s there are in my age. Well, there's 0 and probably always will be, right? If I live to 256, I'll be doing something besides, well, I'll probably not be doing anything, actually. But I was going to say I'll be doing something besides teaching. But I won't get any 256s. That's okay. You know, that's life. How many 16s can I get out of 46? Well, let's see. 16 is 32. 32 plus 16 would be 48. So that's too many. I can only get 2 16s. So in base 16, the first, not the lowest place digit, but the highest place digit is going to be a 2. Right? I'm going to look pretty young here in a second. 46, but I'm going to look like I'm in my 20s. Let's see if I can get away with it. So what did I have? 32, because I got 2 16s. 32 from 46 is what? 14? If I'm thinking right? Yeah, 14. So how many ones do I need? Well, I need 14 ones. Well, the game is up because 14 ones would have to be written as, well, let's see, F is 15 ones, E. So my age is 2E in hexadecimal. So I guess I'm 2E years old. I don't know how you'd say that where it sounds nice. Okay, so the nice thing about hexadecimal is not so much that it can be converted to or from decimal. The nice thing is how it matches binary so well. And here you get to see an example where converting the hexadecimal number into a, and the heading's wrong here, it's actually converting hexadecimal to binary. Converting it is very easy. You just take each digit and that maps into 4 bits. So 7, if I know I need 4 bits to represent that hexadecimal number. So let's see, I don't need an 8. I do need a 4 plus a 2 plus a 1, which would be 7. So that's 0, 1, 1, 1. I need a B. Now what is B again? Well, let's see, B is 11. So if I have 4 binary digits, that's going to be an 8. I don't need a 4, right? So an 8 plus a 2 is 10 plus 1. So that's going to be 1, 0, 1, 1. Okay? A 1 in hexadecimal is just 1 in binary, right? 0, 0, 0, 1. It's important to write those leading zeros. If you're converting from hexadecimal, one of the things we often do is we include the leading zeros. It's really important that you remember that because of the way that these binary numbers are stored in memory. They're stored in packets of, you know, either 8 or 16, and you don't really want to round it off and, you know, say use, you know, 9 of these digits. That doesn't match really well. It kind of shows that you don't really understand the importance of binary numbers. Rather, I would use at least 12, and I would actually prefer to include another nibble at the beginning of this, which would be 0, 0, 0, 0, and then continue with the binary number. In fact, in the hex number, I would prefer to see 0, 1 be 7 as a nod to the fact that, you know, this stuff is going to be stored in a 16-bit memory address somewhere. Now there are variations on this, and we get into codes now. So far we've talked about numbering systems, but now we're going to talk about codes. Codes are different than numbering systems because codes aren't necessarily, they don't follow the rules that numbering systems use, but sometimes they're a useful mapping of numbers. Now binary coded decimal looks a lot like binary, but instead of being exactly like binary, the actual code's a little bit different. The 0 in binary coded decimal matches the 0 in binary. The 1 looks like the 1, the 2 looks like the 2, all the way down to the 9. Notice that at the 9, the binary is 1001, so 8 plus 1 is 9. That makes sense. In binary coded decimal, we have 1001. Okay. Remember I said that binary transforms to hexadecimal really nicely, or hexadecimal transforms to binary very nicely, but that's kind of inconvenient because a lot of times we need to show a human operator a number, and if you show a human operator a number in binary or hexadecimal or octal, they're probably going to be confused pretty quick because they're used to working in decimal. We need to display decimal numbers, but it's not necessarily the most convenient system. So binary coded decimal is primarily used for communication, for displays, for either input from the user to the system or a output from the system to the user. And notice what happens here. In binary coded decimal, we go to 1001, and then rather than using all the other possible combinations like 1100 or the next one, which would be 1010, rather than using all those, we just waste them. We throw them away and say, look, we're not going to take up a lot of memory with this binary coded decimal stuff. We just need a little bit so we can display some numbers for an operator. So what we're going to do is take 1001 to be the last code that binary coded decimal will use, and then it starts back over at 0 and gets a new set of 4 bits. Now why would we do this? Well, because then 4 bits in binary coded decimal maps nicely to 1 decimal digit, you see. So notice what's happened here. When we overflowed in binary coded decimal from 1001 to 0, we got 4 more digits, 4 more binary digits, which represent the 1 in the decimal 10, you see. And so that's why this system is used. Now, it's not all that common anymore. It is still used some. You may find it, you may not come across it, but it's likely to pop up, and so I've mentioned it. And this makes it really easy to go from a decimal number to a binary coded decimal number, or the other way, because what we're going to do is just reserve 4 different bits for 1 decimal number. So if we want the number 3 in the ones place, that's easy. It's 0011. You can still translate it the same way, right? We still have the twos place and the ones place, so that's still 3. And then if we need 6, that's easy. That's, you know, what, 4 plus 2? So that's 6. That's easy, 0110. If we need 8, well, that's easy. We just turn on the 8's position, right? We don't turn on the other, so it's 1000. If we need 9, by the way, we just turn on the 1. The number doesn't call for it here, but it could. And then 7 at the end, well, that's easy. That's no 8's. A 4 plus a 2 plus a 1 is 7. So that's the binary coded decimal. Now be careful, because if you see a binary number and you don't know that it's binary coded decimal, you could make the mistake of interpreting this in terms of binary. This is a very different number in binary than it is in binary coded decimal. Because understand what we're doing is we're taking a nibble and then starting over with the next nibble. Notice that the least significant number here, the thing that represents the 3, that nibble that represents 3, has a 1's place, a 2's, a 4's, and an 8. The next nibble over that is reserved for representing the 6 has a 1's, a 2's, a 4's, and an 8. If this was a binary number, that 0 there in green, that 0 would not be a 1's position. Rather, it would be, let's see, we'd have a 1, 2, 4, 8. It would be a 16's position, then a 32's, a 64's, a 128, right? So we're starting over. We're starting the columns over at 0, so that yes, this number goes together, but it's coded differently than regular decimal. That's why it's called a binary code and not binary counting or binary numbering system. So often when we want to distinguish between these two, what we'll do is put base 2 for binary, and we'll put BCD, binary coded decimal, for a number that looks like binary but is in fact a decimal number simply coded in binary. So let's figure out what this number is. Well, we can read it over there. We take the last nibble, 1001, so that's 8 plus 1, that's 9, that makes sense, they did that properly. The next nibble is 0100, so let's see, it's something like that, right? So there's the 8's, the 4's place, 2, so the 4's place is on, it's a 1, and so we have 49 in binary coded decimal. Now let's figure out what that number would be if we misinterpret it. So I'm going to interpret the lower number that is supposed to be binary coded decimal. I'm going to interpret it as if it's binary. So we've got 8 bits here, right? So we've got the 1's place, we've got 1 on, we've got 8 on. We don't have the 16's or 32's, but we do have the 64's on and not the 128. So if you interpret this as a binary number, you've got 64, right, plus, let's see, 1, 2, 4, 8. So 64 plus 8, which is what, 72, plus 1 is 73. So you might make the mistake of saying, well, this is 73 in base 10. No, it's not. It's a binary coded decimal number. Now the one above, the 110001, that is base 2, that is legitimately a binary number, and of course it ends up being 49 because we've got the 1s on, we've got the let's see, we've got the 16 on and the 32 on. Let's see, so 32 plus 16 is 48, plus 1 is 49. So yes, that makes sense. What if we made the mistake of interpreting the 110001 base 2 number as binary coded decimal? Well, let's see, then that would be 3 off, 1 on. That would be 1 for the first digit, the first decimal digit. The second decimal digit, since we only see 2 on, we've got to assume the other 2 are off. And so we start over, and that would be 1 plus 2 is 3. That would be 31, see? But it's actually 49 in base 10. So you have to know whether a string of 1 and zeros needs to be interpreted as binary or binary coded decimal. There are actually even negative numbers and 2's complements, and that's another coding system, if you will, although it has a lot more in relation to a numbering system. It's at the end of the slides. I'm not going to go through it because a lot of times we really don't worry about that. We don't need it necessarily. But this is not so foreign to you. You probably realize that if you have a thumb drive or a cell phone or anything, that all the pictures you have, all your music, you know at some level it's all stored as a string of 1s and zeros. Well, the way you interpret those 1s and zeros are what give it meaning. Now, it contains meaning, but you have to interpret it properly in order to understand or to interpret that meaning, right? In the same way, you have to interpret these binary numbers in the proper way to understand what they're trying to tell you. I mean, if you take an MP3 file or an OGG file, a compressed music file, okay, and you try to interpret it as a picture, it'll just be garbage, right? It won't make any sense. Now, often the different interpreters that understand what an MP3 string looks like looks for certain markers and knows not to try to interpret something that doesn't have a certain, special sequence at the beginning or the end or somewhere in it, or a certain format and layout. So often the algorithms that try to interpret binary numbers have some way of sensing whether or not the string of 1s and zeros is actually a thing it can interpret, and that's just by convention. Everyone agrees that in a TIFF file, for example, which is a format of picture, if I remember right, it always begins with TIF in Ascii, which Ascii is another coded system. But it's a special string of 1s and zeros, and the interpreter will look at it, it's trying to show you this picture that's in the file, and it'll say, well, you told me this is a TIFF file, but it doesn't have the right markers, so I'm not even going to try to interpret it because it can't be a TIFF file. And if it did try to interpret it anyway, it would just be garbage on the screen, okay? A thumb wheel is really one of the reasons for binary coded decimal. It's pretty common to have thumb wheels on machines where you can enter a number to a PLC, and these are just roll wheels where you can enter the number 0 through 9, and often these come in as binary coded decimal. And so 8, for example, would be 1000. If you roll it all the way up to 9, then that would be 1001. The other combinations are not used, and so you can wire these 4 inputs to 4 input points on an input module and thereby get a number in on the input module. A lot of programs for PLCs have functions to convert binary coded decimal to binary or binary to binary coded decimal. And that's a really convenient thing to have. Some have it, some don't. Binary coded decimal is becoming less and less common, and so it's becoming less and less common on PLCs. But it's still something that you should be aware of. Gray code is another kind of code. It's not exactly a numbering system, but it is a way of using 1s and zeros in certain contexts that is very useful. Rotary encoders are devices that you can attach so that you can sense the position of something. For example, when I redesigned a robot, we had rotary encoders on the back of the motor, and the motor was geared down quite a bit, so the motor would drive the axis of a robot, okay? And it was geared down because you wouldn't want to direct drive the axis. The motor really just doesn't have appropriate torque for that. And so you'd run it through a harmonic drive or other high gear reduction system. But if you measure the rotations of the motor rather than rotations of the arm joint, you can get a much more precise arm joint because it's geared down, right? You got a mechanical advantage there. The problem is that in these encoder type circuits, it's actually ideal to use something called gray code because you only want one bit to change at a time. Notice in the binary column what happens. From 0 to 1, only one bit changes, but from 1 to 2, from the second row to the third row, there's two different binary digits that change. The one's place changes and the two's place changes. And that's not convenient. So in an encoder, it's pretty common for it to give you incremental positions that are 0000, 0001, and then 0011. But so as not to waste the other possible combinations and to continue with this idea of changing only one bit at a time, the next number in gray code is 0010. Now in binary, that's equivalent to a 0011. That's the same number of steps from 0. Okay? And notice in gray code how as you progress through the different numbers, the different codes, if you will, what happens is only one bit changes at a time, and yet we manage to use all the possible combinations that are available to us. Okay? Notice in binary, sometimes only one digit changes, but very often more than one digit changes, and that's what we're trying to avoid. So gray code is one of those things like binary coded decimal that you may or may not come into contact with, but if you're dealing with encoders, you will probably see this at some point. Now they can be used for position encoders, whether it's a rotary encoder or a linear encoder, and these are typically not what's called relative encoders. These are absolute encoders. So each position has a unique code that goes with it. Now honestly, absolute position encoders are not as common as relative encoders these days, so you may or may not see this. But the idea behind using gray code is to minimize error. So here's a picture of an optical encoder disk that has several different positions. You can see that there are 4 bits that indicate each different position. Now we can't tell exactly where the disk is, just within a certain degree range where the disk is. And basically there's just patterns on the disk that can be sensed by 4 separate sensors, and so you always know where they are. But you'll notice that as you go around the disk, these are numbered in gray code. Only one position changes at a time. Ascii code is another type of code that you will probably see. Ascii is actually fairly common these days still. It doesn't stand for American Standard Code 2, it stands for American Standard Code Information Interchange, if I remember right. So it's not like there was an Ascii 1 and then an Ascii 2.0. That's not what this means. And Ascii code is just a way of defining different bit patterns in binary to characters. So it's just a mapping. So if you need the character capital A, everyone agrees that's a, and I'll put it in, I'll add it, a 01000001. Okay? So this is just what everyone agrees upon. It's kind of like a code wheel, right? It's a code book. You have a binary number that you know is supposed to be an ASCII symbol. Well, take 7 bits of it, or actually 8 bits. The original table only has 127 different entries, I think. No, 128, 0 through 127. And so it's 7 bits, but you can extend it to include another bit, since that matches nicely with memory and 8 bits. But everyone agrees that the character capital A is this 7-bit ASCII code. I suppose you could come up with your own code and confuse everyone, or have your own secret code, but it'd probably be broken pretty easily, because this is not intended to be a secretive type code. This is not a way of, like the Enigma machine, encoding something and encrypting it. That's not the point. The point is simply to represent characters that we commonly use in terms of bits. And you should look up an ASCII code table online. I'll try to include a link in the learning module, because you can see the whole table and see how it's set out. So the purpose of this is not encryption. It's really just to map each character. So if you type an email to somebody, "Hi, how are you?" then each one of those characters, HOW, each one of those will have its own grouping of 7 bits that represents that character. So when you type on a keyboard, all your keystrokes get changed into ASCII characters and can be communicated then over protocols and then interpreted properly at the other end. So I promised you that I would teach you how to count, so here we go. Let's start off with decimal. So decimal is pretty easy. You all know how to count in decimal. Well, let's see. We start off with 0 because we have to start from 0. And there's 1, 2, 3, 4, 5, 6, 7. Well, let's try 7, 8, 9. And now we have to roll back over to 0 and get another digit, right? So I probably should have only used 2 different cells or 2 columns here. So let's fix that. Move that over. Delete these. Merge these. There we go. And then, of course, this digit will remain constant for a while as this digit re-increments, indicating the next numbers. But now we're back to 0, and so our decimal number, or our other digit, has to increment at this point. And of course, it will remain constant again for a while as this one increments. We could all go on with this for quite a way. But let's stop at 26 because that looks like the last row before Excel will start scrolling. Now we all understand that the digit here is actually 0 this entire time. We just usually don't write leading zeros in decimal. Now in binary we usually do write leading zeros. So let's see, if I want to represent up to 26, I'm going to need, let's see, 5 different binary digits. So let's go for binary next. And I'll go ahead and reserve 1, 2, 3, 4, 5. Let's see, merge and center. And this will begin at 0, 0, 0, 0, 0. The next one, this is going to take a while, 0, 0, 0, 0, 1. The next one will be 0, 0, 0, 1, 0. And then finally, 0, 0, 0, 1, 1. You might say, well, you said finally. What do you mean by finally? I mean, after all, you got a lot more to go. The next one would be 0, 0, 1, 0, 0. That's true, but notice there's a pattern. Notice that 0, 1, 0, 1, 0 is a repeating pattern. And guess what? This 0, 0, 1, 1 will be a repeating pattern as well. So if you can predict here that the next number is 1, and then 0, then 1, then 0, then 1, 0, we can fill in the rest of these pretty easily all the way down to 26. You should be able to predict here that it's going to be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, etc. And over here, guess what it will be? Well, it will be 4 zeros. So it's 1, 0, 1, 1, 2 zeros, 2 ones, 4 zeros, 4 ones. And since this takes a while to type, I'm going to just copy this, and then I will simply paste it. So I'll just paste it over and over. So then you would realize we get 4 zeros if we need them, but we only need 3 and then we're done. How many zeros do you think we'll have here? If we had 1 here, 2 here, 4 here, well, we're going to have 8 zeros here, aren't we? 1, 2, 3, 4, 5, 6, 7, 8. Let's double check and make sure that makes sense. Should the next one be a 1? Well, as a matter of fact, notice we are out of space here. We've got 1, 1, 1. And so, since that's a 0, we need one more digit, so there it is. And that will remain at 1 for, let's see, 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. We only need 3 more, so there we go. But it would continue with 8 more 1s at that point. And so for this column, we'd have 16 zeros. So let's see, 0 all the way through row number 17, because we started at row number 2. So let's check and see. Sure enough, we're out of space here, right? We need another digit, so we'd need 16 more 1s, but we're not going all the way to the number 32 or 31. And so we'll never get to see it roll back over to 0 unless we continue this pattern. What about octal? Well, octal requires, remember, 1 digit for each 3 bits. So I can predict that octal will only need 2 columns in order for us to go up to 26. Because look, we only needed 5 bits to go up to 26. And with octal, each digit in octal represents 3 bits. So if we go all the way down from here to, the end where we're stopping, we should have enough by having 2 octal digits. So let's see, 0, 1, 2, 3, 4, 5, 6, 7. Now we're out of numbers because that is 8 numbers. 0 through 7 are 8 numbers. We have to start over. In fact, let me just copy this and start over. I mean, that's what I did with binary, right? That's what you do with decimal. You just copy and start over, right? You've got 0 through 9, 0 through 9 again, and so on and so forth. Just like we have 0 through 1, 0 through 1, etc. Okay, so if we just keep copying and pasting this, I'll type the last few, 0, 1, 2. And then over here, well, let's see, it's understood that there's a 0 here until we're out of space in our lower value digit, and so now the next group of 8 numbers gets a 1 in front of it. Okay. Now we're out of space again. The 7 needs to roll over to a 0. That means that the next digit needs to increment. There we go. And then increment again, and there we are. So we've counted up to decimal 26 to 32, its equivalent in octal. The last thing is hexadecimal. Now with hexadecimal we will still need 2 digits, but just barely, because notice one single hexadecimal digit can represent 4 bits. So let's see, hexadecimal. Okay, so I'll need 2 different digits, but just barely, because for quite a while I'm going to have zeros in the more significant digit. Obviously 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but we're not done with the numbers. Now we have A is the next number, B, C, D, E, and F. Now let's make it all look pretty. Let's just center everything. We don't want to merge it, we just want to center it. There we go. And now we start over because we're out of numbers. F is the last number, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and again A. We're not out of numbers yet, right? So this, let's see, we'd have 0 all the way until we run out of numbers there, and then we'd have 1s for the rest of it, because understand, we're not out of numbers yet. The next number would be 1B, which would be 27 in decimal. So that's how you count. And what I really meant was how you count in different numbering systems. Because hexadecimal and binary are really the kings when you're talking about relatively low language or low level operation with PLCs or computers or whatever the case may be, because these things actually work on digital. By the way, there were computers back in the past that were analog computers. There were also computers that used tri-state logic instead of bi-state logic. Probably some used, quad-state logic. But what has really taken over is bi-state logic, 0 and 1s, and so that's what we're familiar with and use today.